Before we dive into quantitative phase analysis, we should first introduce the main method used for this purpose, the Rietveld method. This lecture describes the basic principles of the method and builds further on the insights into X-ray powder diffraction that have been treated in lecture 2. The Rietveld method was originally developed by Hugo Rietveld in the late 60s. This was done for the refinement of crystal structures using neutron powder diffraction. Only later, in the 70s, it was extended to X-rays, and even later, like in the 80s, it was eventually extended to quantitative phase analysis. For cement analysis, the first application of the Rietveld method dates back to the early 90s. The Rietveld method now finds its use in a wide variety of areas as a characterization technique for crystalline solids. Next to its use in quantitative phase analysis, the method can be used to derive or refine crystal structures for pure powder samples. Also, crystallite size and strain can be determined through peak shape analysis. In fact, many key properties of solid systems can be studied by Rietveld analysis. Kinetic studies, for instance, of reactions occurring during cement hydration or polymorph transitions, thermal expansion behavior of ceramics, in situ chemistry, and phase transitions can be analyzed easily using the Rietveld method. To do this, the Rietveld method minimizes the difference between observed and calculated patterns at each data point I in the diffraction pattern using a least squares approach. Here, the sum of the statistically weighted square differences between the observed and the calculated intensities is minimized over the whole pattern. The calculated pattern takes into account crystal structure information, phase concentrations, and other sample characteristics such as microtexture, but also diffraction optics and instrument-dependent parameters such as X-ray source, etc. are being taken into account when calculating the X-ray powder diffraction pattern. The calculated intensity at a given data point in the diffraction scan is obtained as a sum of the contribution of the background and all neighboring reflections P of all phases J in your sample. This is also expressed in the mother equation of the Rietveld method shown here. Here one can see that S of J is a scale factor, Lp is the Lorentz polarization factor, F is the structure factor, G is the peak shape function, A the X-ray absorption coefficient, and P the preferred orientation correction. In lecture 2, we have treated each of these factors in more detail, and we have explained what is the physical basis of these factors. Now, before we go into a demonstration and practice, it is worthwhile to reflect on what we really can call a good fit, and how we can actually evaluate this. This is needed because we want to check that we're going in the right way when doing the fitting. And there's also a need to be able to compare between different measures of goodness of fit, and maybe we also want to do this, to be able to do this independent of the quality of the data. To this purpose, the most direct way of checking if a fit is good or going the right way is by actual visual inspection. While this is by any means the most powerful and direct way of evaluation, it is also the most subjective way. What is, for instance, good in one student's eyes may not be so for his supervisor. Numerically assess the fitting, several numerical parameters of factor or indices are available. Depending on the material itself, the data quality, and the purpose of the analysis, one may prefer to use residual or R factors, or the chi or goodness of fit indicator, or for instance the Durbin-Watson statistic. Sometimes a very good fit is obtained by allowing very large shifts in crystallographic parameters such as unit cell parameters, or in crystal structure refinements, atomic positions. In these cases, it is good practice to always check whether the obtained crystal structure is chemically reasonable. For instance, it is known from a great many of experimental data and from chemical bond theory that a tetrahedral silicon-oxygen bond should have a length of about 1.6 angstroms. Very large deviations, for instance 1.8 angstroms, are therefore quite suspicious and would require further analysis and verification. This slide shows the mathematical expressions of some of the numerical agreement factors. The pattern residual and the weighted pattern residual describe the agreement between the observed and calculated pattern at each data point in the profile. The residual pattern is therefore much affected by the signal-to-noise ratio, the background noise level. The residual weighted pattern therefore accords a bit more weight to the actual signal or the peaks to mitigate this dependence, but still it is much influenced by the quality of the data. To remove this dependence entirely, one can use the goodness of fit indicator that normalizes the weighted pattern residual by an expected residual. This expected residual is an index that is calculated for a best achievable data fit of the data. While the pattern residual and the weighted pattern residual should reduce as much as possible during the fitting, the goodness of fit indicator should obviously converge to a ratio of 1. On the other hand, there's the Durbin-Watson statistic, and this is applied to residuals of least squares analysis to detect any ways of autocorrelation between the data. If the value is close to 2, then there are no indications of autocorrelation. If there are actually indications of autocorrelation, then measures to increase the signal-to-noise ratio or resolution should actually be considered. Let's have a look at how a Rietveld fitting operates in practice. We will show here some snapshots of a Rietveld refinement of a simple two-phase material consisting of halide and rutile.
To continue with the Rietveld method, we should have already done the identification. With the results from the identification, the related crystallography information file, namely the CIF file, must be found to perform the Rietveld analysis. The file can be found in the commercial database, such as Inorganic Crystal Structure Database, the ICSD, or the open database such as Crystallography Open Database, the COD. First, create a new file, then insert the data. According to the identification we did before, the mixture is made of calcite and quartz. Firstly, we import the structures. Let's change the name, calcite, and then quartz. For each phase, the scale factor, unit cell, and profile should be defined. Constraints of 1% of variation on the unit cell were applied to secure refinement. Another constraint for the profile W of 0.0001 to 0.2 was applied. The application of constraints to the refined parameters will improve the stability of the overall refinement, when especially we are analyzing complex sample such as the hydrated cement. Do the same settings for quartz phase. For the global parameters, the specimen displacement, background functions are refined. For the background functions, we use the polynomial function together with the flat background, 1 over x, together with the 5 coefficients. We use the manual mode for refinement as we set the parameters manually. After all the parameters are set, the refinement can be executed. Open the additional graphics for the difference plot to visually check the fitting. Change the y-axis to square root to show more details on the small peaks. You can evaluate the fitting by checking the agreement indices, namely the R profile, weighted R profile, and the goodness of fit. The aim of the refinement is to decrease the residue of the fitting. Thus, the value for R profile and weighted R profile should be the lower the better. Typically, 5 to 15% for the weighted R profile is acceptable for most of the cases. Theoretically, the goodness of fit should be 1. Practically, a value of 1 to 5 can be acceptable depending on the case. Now, the goodness of fit is 5.9 and the weighted R profile is 16.6. If you check the residue plot, the fitting at around 27 and 13 degrees is not so good. This can be because of the preferred orientation. If you locate the mouse on the peak which is not well fitted, the crystal plane of the peak will appear along with the name of the face. Here it is a 104 plane for calcite. To set the preferred direction, you can click on the calcite in Refinement Control. Then, in Object Inspector for calcite, you will find the item called Preferred Orientation. The Match-Dollars model is recommended. Specify the direction HKL of the plane for the preferred orientation. After setting the direction, check the refine for the Match-Dollars factor. Similar to the other parameters, we put a limit for the refinement of 0.7 to 1. The value 1 means there's no any preferred orientation. The smaller the value, the higher the preferred orientation. In most of the cases, 0.7 should be enough. If value is too small, which means the sampling is not well done, a repetition of the XRD data collection with more attention on reducing the preferred orientation is recommended. By refining, the fitting of the peak is much improved. Do the same for the preferred orientation of chords. The plane of the chords is 1, and then refine. There is some improvement for goodness of fit and the weighted R profile. As you can see, there are still some misfitting for the peaks of calcite and quartz. For calcite and quartz binary mixture, to achieve better fitting, more profile parameters needed to be used. Let's try all the profile parameters for quartz and calcite. Refine again. The fitting is much improved by using more profile parameters, and the calculated weight percentage for the calcite and quartz are getting closer to the weight amount. Save the HPF file, press the button Weight Percentages. You will have the quantitative data output in TXT file in the default High Score Plus folder, or simply load down the results from the graphic window.
This is our X-ray diffraction scan, measured on a conventional lab diffractometer using copper K-alpha radiation. We can see a multitude of peaks, some single, others overlapping. In a first try, a background function is fitted, and the first residual is calculated, as you can see below the graph. Obviously, this residual is still very high because we have not fitted any of the Bragg peaks. In a second step, we introduce rutile into the fitting procedure. Now you can see that only the intensities or the peaks of the rutile are being fitted, and this is done by adapting the scale factor. You can see that the residual has decreased. Then we will introduce halide as triclinic tricalcium silicate into the refinement. Again, you can see that only the intensities of the halide are fitted. And the agreement index drops again, but you can clearly see that there is still a visual mismatch of some of the halide peak. We then allow the halide and rutile lattice parameters to be refined together with the scale factors of each as well. Now, we clearly see that the weighted pattern residual drops drastically, and that there is already quite a good fit when looking at the residual. This residual curve in gray below the diffraction scan helps to spot slight mismatches and see where there are some deviations from the nil. Now we also refined, in the next step, the peak width for both halide and rutile. Again, you can see that this significantly improves the fitting, both in the residual as in the visual appearance. Further fine-tuning of the Rietveld refinement can now be done, for instance by adding the atomic displacement factors from the literature data. Then finally, we can include a preferred orientation correction for the halide phase to achieve our final fitting results. One can now see that the fitting is really nice and that the residual curve is quite flat. In the case of this sample, we then actually had about 27% of rutile and about 73% of C3S, triclinic C3S in this mix. This example shows that the parameters that we vary in a quantitative phase analysis are first so-called global parameters such as the background and a sample displacement correction, and then second, phase-specific parameters such as scale factors that will fit to the observed peak intensities, unit cell parameters that will fit to the peak positions, and peak profile functions that will fit to the shape of the peak. The use of intensity corrections, such as preferred orientation functions, may be necessary, but will be included later in the refinement always. The refinement of other crystal structure parameters, such as atomic positions, site occupancies, or atomic displacement parameters, is not recommendable for complex mixtures of phases such as cements. This is because this may lead to wrong results due to strong correlations in parameter variations during the fitting, as the ratio between variables and independent data strongly decreases and the minimization problem gets under constraint.